old coffee out there, didn't you?
No, they took those away all the time.
No, we'll see. We will decide. Yeah, we'll decide at the end of the morning, I guess.
Whatever you're going to do, they'll bring the coffee around.
Yeah, we'll be here at 2.
Yeah. Should I go? 9:01. Wait 2 minutes. Start slowly. Okay, so let's start. Let's continue from where we stopped yesterday. So we saw that when we describe gravity, instead of in terms of metric, in terms of a Wilbein and a spin connection, then it's natural to combine these two objects, which can be viewed as one forms. It's natural to combine them into a single one form W. Which is viewed as a gauge field of the ADS algebra in the case, let's write it like this, the ADS algebra in the case of negative cosmological constant, and now here the notation small d will be the dimension of the boundary. Okay, so this is the isometry algebra of ADS-D plus 1. Okay, so this PA and MAB are the generator of this algebra. I wrote the algebra yesterday. Is as I said, is the ADS algebra, or equivalently is the conformal group of a CFT in d dimensions, right? So these generators here that are written as local translations and local Lorentz, they can be, if you repackage them, this algebra is exactly equivalent to the algebra in the CFT of translation. Now let me use slightly different notation. Translation, rotation, dilatation, and special conformal generators, right? The algebra of these operators, these generators, which is the conformal group in the dimension, is the same as that algebra that we wrote yesterday, okay? Well, some relation is obvious. For example, Mij will be the ij part of this generator, pi will be the pi part of that generator. Other generators are linear combinations, okay? So these are the generators that you can get from the conserved current at spin 2, which is the stress tensor. So now the idea is try to generalize this to higher spin, understand how to do a Wilbein formulation of higher spins, and view the corresponding objects at some gauge field of enlarged algebra, which will be the higher spin algebra. Okay, so we first need to understand what is the analog of these objects in the higher spin context. Okay. Actually, I still have a lot of space here. So we basically want to know So when we write Franzdal equation, we describe it in terms of totally symmetric field, which was double traceless. We want to know how to describe this in terms of some higher spin Wilbeins. Okay, and so we knew so far we just know how to describe linearized field. So we will just try first to derive a map between this linearized field and some linearized Wilbein. And to do that, we just recall how it works in the case of spin 2 and try to generalize it. So in the case of spin 2, we describe fluctuation of the metric in this form, right? We have a background, which, let's say in this case, will be ADS plus a fluctuation, right? And if we want to write down what is this fluctuation in terms of the Wilbein, well, we do a corresponding decomposition of the Wilbein. Let me call the background bar, okay? Plus the fluctuation, E tilde E mu A. Now you just use the fact that the metric is eta A B E A nu E B nu, right? That's an exact relation. You plug this perturbative decomposition into that, and you find the relation between the linearized graviton and the linearized Wilbein, right? So that's standard. Let me not do the calculation. So this gives that the relation between linearized field is just that the linearized spin 2 field is nothing but the symmetric part of the Wilbein where this object with both curved indices is just obtained from the linearized Wilbein by using the background Wilbein. Okay? So the spin 2 field in the description, like Franzdal-like description, where we have a totally symmetric field, is just the symmetric part of the Wilbein, essentially. You have to lower one index to make the flat index into a curved index using the background Wilbein, but essentially it's the symmetric part of this matrix. Okay? So we know, of course, that the anti-symmetric part of this matrix drops out because it can be gauged away by local Lorentz rotation. Right? So the anti-symmetric part is the extra components that the Wilbein has compared to the metric. It doesn't appear in this map. It's only the symmetric part that appears in this map. Okay? Sorry. So now we just generalize this. So we want some, again, some kind of one form. We want a one form that we can put into a gauge field. And we want something which, after we do a similar procedure to this, gives us a totally symmetric field with S indices. So the natural guess for what the higher spin Wilbein is supposed to be is just a one form again with some internal flat space indices. How many of them we need? For spin S, well, we would need S minus 1, right? So, and then we will identify the Franzdal field, which is totally symmetric, as the symmetrized part of this matrix after we convert these indices into curved by using the background Wilbein. Okay, so this will be E mu1, mu2, mu-s, totally symmetrized. Okay. Now this object here is totally symmetric and traceless in these indices, so it satisfies this. So in terms of the Wilbine, this is just some very natural, irreducible representation of the rotation group with a totally symmetric, traceless representation. And it follows that if this is, if you assume that this is the correspondence to the Franzdal field, it follows that this is double traceless automatically. Okay, so that strange condition that you have to impose in Franzdal equations, it basically can be, it follows if you start from Wilbine description and identify the Franzdal field as the symmetric part. Okay, so because this is traceless in these indices, if you take one trace, you're not sure that this is 0, but if you take trace twice, you must at least trace 2 of these indices here, so you get double traceless. Okay, so double traceless is automatic. Okay. Now, in the same way as the spin 2 Wilbine has more components than the actual physical spin 2 fluctuation, because it's just a symmetric part, which is related to that, this description also will have more components than we actually need, right? So in the same way as we had to introduce some local Lorentz symmetry there and introduce a spin connection, here we have to introduce some spin connection-like objects, which will allow us to gauge away the extra component. Okay, so this is a little bit technical to do it all in detail, and we don't have time. So I'm just going to claim what is the final result. What is the generalization of a Wilbine spin connection in this context? Okay, Wilbine is clear to understand. What is not totally clear is how many spin connections you need and what kind of spin connections you need. So let me just claim what's the result. I'll put it here. So for spin S, we need, well, we already said we need the spin S minus 1 Wilbine, and then, well, you can guess that you first will need an object like that. That will be the first guess. That will be a generalization of spin connection. You add an extra index here. So this is totally symmetric here with S. This representation with a comma means this. So S minus 1, in this case just 2. Okay, but then if you do this, you'll see that this allows us to remove the extra stuff here, but this guy itself has some redundancy which you have to remove. So you have to go on and introduce another spin connection. So you have another one, B1, B2, and you go on until you reach the last one. Okay, so these are all the fields that we need. Schematically, let me write it like this. So this is what you need in the frame-like or Wilbine-like description of higher spin field. And now what is then nice, what one can check, is that this structure precisely agrees with what we expect from CFT. If you count how many of this one form we have here, you count how many are there, the number of total one forms is the same as the number of generators of the higher spin symmetry at spin S. In the same way as here, we have total number of one forms is the same as the dimension of the conformal group, which is the number of conserved charges that you get at spin 2. This collection of objects is, we have as many one form as generators at level spin S. Okay, so all the generators that you can build in the CFT from the spin S current. Again, this takes some time. We can discuss it later if you want to know more. But let me just claim it here. We have the total number of one forms is the same as the total number of higher spin symmetry generators in CFT. So these are all the symmetries that you can construct out of the higher spin current.
How do you
Okay, since you ask, let's just to quickly do it. So right, so let's recall spin 2. So at spin 2 we have the stress tensor, and you can build a collection of conserved current, spin 1, labeled by some conformal killing vector psi, which is nothing but Tij psi j. And for any, so conformal killing vector will be an object which satisfies the killing equation up to a divergence term, right? And what do I need to put here? Delta ij over d with a factor of 2, right? That would be the conformal killing vector. And you know that in flat space there are as many solutions as these as the generators of the conformal group, right? Some of them are just ordinary killing vectors, translations and rotations, and then there are extra conformal killing vectors, which are the dilation and the special conformal transformations. Okay, so we have as many of these currents as the dimension of the conformal group. Okay, and for each of this current, you can construct a charge in the usual way. You integrate the time component of this over a spatial surface, right? Okay. Now for higher spin, there is a similar construction. So for general spin S, we have the conserved currents. Now I'm using I instead of mu because I'm using mu for the bulk. Okay, that's why I'm using this I. In the first lectures, I was using mu and nu for the CFT. So we have these guys that are conserved. We can construct a current labeled by a conformal killing tensor of rank S minus 1, bigger. So that's just a contraction of this current with a, maybe I should call this I2, IS, psi I2, IS, okay, where this object with S minus 1 indices is a conformal killing tensor. Okay, and if this conformal killing tensor is an object which satisfies an equation similar to this, so if you take the derivative on this and totally symmetrize with respect to all indices, you get something which is 0 up to trace terms. Okay, so that's, let me now write it down. You understand the definition is a simple generalization of this. If that satisfies this, then this is an ordinary conserved current. And you can build a charge in the usual way. And you have as many charge as conformal killing tensors you have in flat space. And you count how many you have. Actually, in flat space or in any conformally flat space, conformal killing tensors are just tensor product of conformal killing vectors. Take an S minus 1 tensor product, symmetrize it, and you count what's the dimension, how many you have. It's the same as that. Okay. All right, so okay, so let me just clarify one thing. A couple of lectures ago, I wrote conserved charges associated to higher spin current. I just wrote one of them, one very simple one in which this conformal killing tensor is just basically the product of S translation killing tensors. And then that is just literally taking this, putting it to 0 this, and integrate. That's what I wrote if you look back in the notes. But you have more. You have more because you can also consider products of more general conformal killing vectors. Questions? Yeah. These higher spin symmetries. Well, they are symmetries which have S derivatives. So the simplest one would be something that acts on this field as derivative along some time-like direction s minus 1 times. This is obtained if you take this to be the product of s minus 1 xi minus, where xi minus is translation along x minus. Then you get this. But you can get something more general if you take also those more the other x-dependent conformal killing tensor that you have here. But in general, they are symmetries with higher derivatives like this. Okay. So this is all from the CFT point of view. Okay, that's what I'm writing here. Okay, so we see that this construction in terms of Wilbein naturally fits what we wanted to do. We want to combine all these objects into a single W. So let me now write it schematically like this. Where this omega s, for any s, this omega s will be a collection of Wilbeins and spin connections, all the ones that we need. So for example, for spin 2, that's just what I wrote before. This omega would be E, the usual Wilbein and spin connection. This guy would be a collection of P and M, right? And for higher spins, we have all those and the corresponding generators. Okay? Okay. So, any questions before I go on? Right, so you could, that's what I'm going to say next. You could define those T's as the algebra that you can compute from the CFT. That's fine. But Vasiliev formulation actually proposes to realize explicitly these T's as some extra coordinates in my theory, impose some non-commutative star products on those coordinates in such a way that the right algebra just comes out as star commutators. So that's what we're going to discuss next. Okay, so you could proceed from here and just work with abstract Lie algebra generators. If you know what their algebra is, you go on. But in Vasiliev formulation, we want to actually now have some very explicit realization of what these T's are in terms of some extra coordinates that we will add in the theory. Okay? And this can be done in any dimensions, but it becomes simpler in 4 dimensions, where the realization of these T's in terms of the internal coordinates is simpler, because we can use spinor formulation. So what I will do next is just now focus on the case of 4 dimensions, so 3-dimensional CFT, and describe what is the realization of these T's. Okay? Okay. So now focus on D equal 3 or ADS4. Okay. So I'm saying ADS4 loosely. Of course, the equation I'm going to write are background independent. ADS4 will be a solution, but the space-time in which the higher spin live is 4-dimensional. Okay, that's what I mean. So here we can use the well-known vector spinor dictionary, right? That you are very familiar with from Freddy's lectures and all of that. You know that in 4 dimensions, you can always, for any vector VA, where this A is 0, 1, 2, 3, you can associate a bispinor, right? V alpha alpha dot, which is VA sigma A alpha alpha dot, where this, I guess this should be, no, that's fine. Where this sigma A are essentially identity and the usual Pauli matrices, and alpha alpha dot are the indices of that matrix. Okay, it's a 2x2 matrix. Alpha and alpha dot goes from 1 to 2, right? So, for example, in this language, what I was calling Wilbon EA is just now will be E alpha alpha dot, and so be careful that I'm just converting now indices in the flat in the local frame. This is still a one form here. I'm not touching the one form. Okay. So EA will be E alpha alpha dot, and the spin connection, you can also work out what it becomes in this two-component language. I think you probably all know this. So you know this is an antisymmetric tensor in 4 dimensions, right? So it's the antisymmetric representation of SO4, let's say. What does it translate to into SU2 cross SU2 language? Does anybody know this already? What's an antisymmetric tensor in the SU2 cross SU2 language? Right. So, in other words, the field will split into two fields, which are omega alpha beta and omega alpha dot beta dot, where these are now just symmetric. Okay? Symmetric and symmetric. Okay? So, of course, you can count, right? This one has 12 components, right? Sorry, 6. I didn't divide by 2. 6 components, and this one has 3 plus 3, right? So this is the self-dual and anti-self-dual part of this antisymmetric tensor, right? So that's the usual story. Okay. Before I write down what the higher spins are in this language, let me write down here some conventions. So when we use this two-component spinor notation, we can lower or higher these indices by using epsilon tensors, right? That's the natural metric for those indices. And we can take, for example, this convention. Same for dotted, and indices are lowered and higher according to these conventions. Okay. Notice that this implies that if you have that it implies that the natural scalar product between two objects is antisymmetric, right? This is equal to minus minus W alpha V alpha. Okay, because it's with the epsilon tensor, and in particular, V alpha is equal to 0 if V is a commuting object, right? Okay. And let me not write down the conventions of the Pauli matrices. You can get them from the review. Let me just tell you what this higher spin field, maybe I'll leave this here. Okay. So this is an exercise, and it's basically, you can do it with Pauli matrices, or you can look at group theory tables and see how representations of SO4 translate into representation of SU2 cross SU2. And you can see, for example, that if we look at this object, which is the spin equal 3 Wilbein, right, that goes into E alpha 1, alpha 2, alpha 1 dot, alpha 2 dot, where these are just totally symmetric in these indices and totally symmetric in these indices, right? And so, for example, and in general, what we can see is that this collection of fields that I have here this T1, 2 up to S minus 1 goes into something relatively simple, goes into an object which I will call W alpha 1, alpha 2, alpha S minus 1 plus N, alpha dot 1, alpha dot S minus 1 minus N, and going from minus S minus 1 up to S minus 1. Okay, so all these objects are collected into this guy. The N equals 0 is just the Wilbein. This is the Wilbein. So in this case, literally, you can just remember that each of these indices split into an alpha alpha dot. Okay, and all the others from minus S minus 1 to S minus 1 are all these spin connections. Okay, so again, to check that I didn't write something crazy, you can check spin 2. For spin 2, we have just the alpha plus N, alpha dot minus N, N equal to minus 1, 0, and 1. 0 is just the Wilbein, E alpha alpha dot, plus 1. Oh, this notation is a little stupid. Sorry. Alpha 1. Okay, let me now write it like this. So for spin 2, we will have alpha dot, alpha beta, which is the N equal 1, and alpha dot, beta dot. Okay, so these are the Wilbein, and those are the spin connections. Okay. Okay, so again, this is nothing too complicated. It's just a matter of translating the representation in vector notation to representation in spinor notation. But the advantage now of this well, there are many advantages, but one advantage is that these representations are kind of simpler, because here we have to impose some traceless condition on these indices, not just symmetrization. But here now, we don't have any traceless condition. We just need to impose that these are symmetric. Totally symmetric here and totally symmetric there. Okay. This will allow to package all these fields in a simple way. Okay. So now that we understand more or less how to write down these fields into component notation. Now we have to basically realize what these generators TS are in Vassiliev formulation. So we introduce this twistor auxiliary variables. And star product. Okay. So let us just introduce a pair of indices, a pair of coordinates, y alpha and y bar alpha dot. Okay. This will be commuting. Well, so for example, if I have an ordinary product y alpha, that's 0. Okay. So these are commuting objects which transform in the spinor representation, so I'll call them twistors. Okay, so these are twistors, y alpha and y bar alpha dot. And now we postulate some star product. Well, let me just write it down, and then we'll see why this is the correct definition. Same for dotted. Okay, and the star product of y and y bar is the same as ordinary product. Okay. So introduce this coordinate and postulate that there is, introduce this star product. Okay, this star product. So this is just how it acts on monomials. If you want to know how it acts, in general, so on general functions, it's just the familiar expression, and put here exponential of epsilon alpha beta d dy alpha d dy beta. This acts here and this acts here, plus the dotted, similar expression with dotted, times g y bar. Okay, that's the usual star product. So for example, something that is useful, and you can, if you want to, well, if you have some interest in practicing with these star products, you can check identities like this. For example, if you take the star commutator, by which I mean y alpha star f minus f star y alpha, you just get 2 df dy alpha. Okay, and the similar identities you can get for bilinears. Here you get 2 y alpha df dy beta plus 2 y beta df dy alpha. Okay, so this, if you want to have fun for 3 minutes, you can try to check them. Okay, so once we have introduced the star product now we see that if we define m alpha beta to be y alpha y beta, m bar alpha dot beta dot equal to y bar alpha dot beta dot, and the p alpha alpha dot to be y alpha y bar alpha dot. Define these bilinear objects. Now it's easy to check that with this definition of star product, all these objects satisfy an algebra under star commutators, which is nothing but the SO3,2 ADS algebra that I wrote before in vector notations. So you will get M alpha beta, M gamma delta. So now what before was an abstract Lie algebra commutator, here it's realized explicitly as a star commutator. This would be epsilon beta gamma, M alpha delta, plus minus other terms, etc. Right? And P with M star commutator will give a P if you use the rules, and P with P star commutator will give a M. Okay, so that's the structure of the SO3,2. Now I'm specializing to four-dimensional space-time, so the ADS algebra is 3,2. It's just the same algebra translated in two-component spinor notation. So what was MAB splits into M alpha beta and M dot alpha dot beta dot, and what was PA become P alpha alpha dot. But now we can realize them explicitly in terms of these auxiliary variables. Okay? Any questions? Okay. Where's my cup? Somebody stole my cup. Okay. So any question before I go on? Okay. So now we see that so at spin 2 level, what I was writing before as W equal to EA PA plus 1/2 omega AB MAB now becomes just I take W, which is a function of X, and also of some auxiliary variable Y and Y bar. And it's, if I want just the spin 2 part, this will just be a bilinear. Right? So this, where P and M are abstract, can also be written as this, where P and M are realized in terms of the Y's, and commutators become star commutators. Okay? Yes? Yes, yes. So yes, whatever was a product of generator in the abstract language becomes star product in this language. So there is a star exponential. You can exponentiate generators, and you can do usual manipulations if you just use the general rules for star product on general functions. Okay, so now in this language, generalization to spin S, to all spins, becomes very, well, almost obvious. We just allow this W to be a general function of Y and Y bar, right? And that will include all this. In the expansion, you will get all these objects. Because these are just the commuting objects, you'll just select this totally symmetric representation, right? So all spins, we just have this. It's just some arbitrary function of X, Y, and Y bar. It will have a Taylor expansion in powers of Y, right? So we can write that expansion as sum over n m from 0 to infinity of W alpha 1 alpha n alpha dot 1 alpha dot m y alpha 1 y alpha n y bar alpha 1 dot y bar alpha dot m, right? And let me call this n m, and well, conventionally you may put a factorial here. Okay. So if you look there at what are the spin S part, the components of this spin S will be the one which has n plus m equal to 2s minus 1, right? When n plus n is 2s minus 1, you get all the spin S stuff into those terms, right? Again, for spin 2, that would just give you the bilinears. It's when the sum of undotted and dotted is equal to 2, you get the bilinears. For spin 3, sum of dotted and undotted is equal to 4, right? So you get in particular that guy there, the spin 3 Wilbein, and then you get when y's and y bars are not the same number, you have the spin connections. Okay? So I'm writing here again. The actual Wilbein, it's always the one which has same number of dotted and undotted components. So that will be this guy. Let me write more explicitly, completely explicitly. And it's still a one form. So remember that there is still everywhere a one form here. Okay. So this object is what corresponds to E A1 AS minus 1, which is what at the end of the day corresponds to my totally symmetric double traceless Fronsdal field, if I go back to the traditional Fronsdal description. Okay. So is it clear? So I tried to spend some time explaining what's the logic of introducing these y and y bars. Is it more or less clear what's the logic? It's just that we want to realize in some convenient way the higher spin symmetry generators. Okay? And one natural way to do it is to enlarge the space by introducing some extra directions, y and y bar. Yeah, it's the algebra generated by. So let me write it down here. Yeah, there is a way to write those higher spin generators in the CFT in this language using these twisters, but I don't want to do it in detail because it takes some time. But at the level of counting how many you have, that's easy to see that they are the same. So here the higher spin symmetry generators are all the monomials y alpha 1, y alpha n, y bar alpha 1 dot, y bar alpha dot m with n plus m equal to 2s minus 1. Count how many you have of these objects, which are, so here totally symmetric. They are the same number as what you get if you count conformal killing spinners, tensors in the CFT. Okay, so this algebra, the higher spin algebra, can be realized. So is algebra of these monomials with star commutators. And this realization is isomorphic to just finding the higher spin charges in the way I explained before, and doing the usual Lie algebra commutator. You get the same algebra. Again, technically, well, it will take me some time to explain it, but at the level of counting, you can see that this is the same. So the spin 2 part, again, is this one. Okay, so once we have combined all these things into a single gauge field like this, then it's natural to define curvatures or gauge transformations of this field just by using usual gauge theory rules. So the curvature would be dw plus w star w. We have to take the star. And the gauge transformation would just be delta w is Tx epsilon plus star commutator of w with epsilon, right? Where now epsilon itself will be a function of x and y bar. So if you expand it, each of these epsilon will have components of all spins. Now they're all packaged together into this single gauge transformation formula. At the linearized level, this once you translate back to Fronsdal formulation, this is the usual linearized Fronsdal transformation, but this gives a natural way to just define it in general in a nonlinear theory. Okay? This W doesn't have to be now a linearized field. We could keep quadratic terms, right? Okay. Now, when we do this at nonlinear level, we will end up having to compute commutators of generators of this type of different spins, right? And that's where we see the fact that we need all spins in this theories. If you look at what the algebra of these objects is under star commutators, schematically, so higher spin algebra structure schematically, if we take commutator of, well, star commutator of two generators. Now this TS1 involves several generators, okay? It could be either one of them. The structure is that you get, well, just apply the definition of star product. You get a structure of this kind. So the star commutator of spin 1, S1 and S2 gives a sum of generators of all the spins. Now you see that if you take, well, for example, let's take the simple case in which we have equal spin. Commutator of TS with TS gives T2S minus 2 plus T2S minus 4 plus up to spin 2. Okay? And you see that if you take spin 2 with spin 2, you just get spin 2. But if you take something of higher spins, you produce something of even higher spin. Okay? So if you take spin 2 with spin 2, you just get spin 2. Okay? These equalities are schematic. It just I just mean which generator appear on the right-hand side. But if you take okay, but if you take, for example, spin 3 and spin 3, what you get, according to that rule, you get spin 4 and spin 2. once you have a spin 4, now you have to worry what spin 4 does. And for example, you can see that spin 4 with spin 4, just with itself, it will produce 36 plus Q4 plus Q2. And so you are forced to introduce an infinite tower of them if you want these gauge transformations to be consistent. You cannot truncate, because when you take these commutators here, when you have a spin S1 component in this W and spin S2 component in this epsilon, you're going to produce higher components, which means that you will generate higher spin components from the gauge transformation. So for the theory to be consistent, you have to include all of them as soon as you introduce something greater than spin 2. So the spin 2 part, this is SO3, 2, and this is just it's the largest finite subalgebra of this higher spin algebra. There is no other truncation. Well, there is a truncation to an infinite subalgebra, which is the minimal subalgebra. You can take just even spins. This closes, okay? Because if you take commutators of 2 even spins, you never generate odd spins. But if you generate a commutator of odd spins, you generate even spins. So you cannot truncate, for example, to an odd spin theory. That doesn't make sense, okay? Okay, any question? Thank you. Indeed, I forgot something here. So if we have, where can I go? Let's go here. In bosonic higher spin theory, we impose that W is a even function. Okay, so objects which have a even number of total even number of y bar are integer spin fields. In this expansion, if I retain the most general dependence, then I can also have half integer spins. For example, an object W mu with just a single index alpha would be a spin 3/2 field, right? I can do that at this linearized level. There is no problem. But in the nonlinear theory, you have to impose this for consistency. And if you want to do the actual supersymmetric version, or even non-supersymmetric, but with fermions, you have to introduce some extra actually variables. It's not just enough to take W to be the most general form. Okay. So since we're discussing here mostly bosonic, we impose this as a constraint. Okay. So there are only integer spin generators and only integer spin fields. Okay. So as you can see, this takes a long time to explain, and we are still not done. We are far from done. Okay, so now we have understood how to encode all higher spin fields into some natural object Y. Okay, but if you remember in the dualities with CFTs, we always had one scalar operator in the operator spectrum, and that scalar operator doesn't appear here. Okay? Here there is no scalar. The term which is independent of y and y bar is just a spin 1 field. So this decomposition includes spin 1, spin 2, spin 3, no scalar. So for having a scalar, you can guess that we will need an extra field. So we need 1, extra field, and you can guess that this field will be some scalar which depends on x, y, and y bar, right? And so this will be a scalar. It will have itself decomposition in all possible powers on y and y bars, and it's natural to guess that the lowest component is just the scalar field that we need, the one which is dual to the scalar operator in the CFT, right? So this will have a decomposition. Save chalk. Let me write it schematically like this. Okay, you understand what I mean by this? I'm just not writing all the indices, but this is like B alpha 1, alpha 2 up to alpha n, alpha 1 dot, alpha 2 dot up to alpha dot n, and those are product of n y's and y bars. Okay, so this is indeed what we need, and the scalar field is B0, 0. This guy is the bulk scalar field, and well, this for now is just a claim. It will turn out that component this and this are higher. They're related to their higher spin curvatures, which are essentially S derivatives on the Fronsdal field. Okay. This, of course, just, well, it comes after you write down the equations and analyze what are the solutions to the linearized equations, which I hope we can at least briefly describe soon. Okay. Okay, any questions before I go on? Now I need to introduce even more machinery. Any question? Okay. Anybody ever see this already? Some people I know. Okay. Okay, so this seems all nice. Relatively, we can basically have some simple way to package all the fields that we need in our spectrum in these two objects. The y and y bar have some natural interpretation as the gauge symmetry generators. Now we want to write down a nonlinear theory with these fields. So historically, what Vasiliev did first is realize that if you use this w and this b just with y and y bar dependence, you can write down a system of linearized equations which in just 2 lines encode all the Fronsdal equations for all spins. Linearized level is no problem. But then the problem arises when you try to make that nonlinear. And it turns out that it's hard to make it nonlinear just by using these 2 fields. You have to introduce some extra auxiliary directions, which somehow technically allows you to write down nonlinear equations in an easier way. So historically, as I said, Vasiliev realized how to write down linearized equations, and then from there he started making nonlinear and realized that he needed more stuff. So I'm going to skip that historical order and just tell you what is the stuff that you need to write down the fully nonlinear equations. Okay? Now, for this extra stuff, I don't have a very natural interpretation or explanation of why you need it. In the case of the y and y bars, it's clear why you need it. You just need to realize the higher spin symmetry generators. Now we need to do something a little more. So, fully nonlinear theory. Okay, so there are 2 steps. Step 1. So we started with all fields depending on the space-time and this auxiliary direction. Now, technically, as I said, the resolution found by Vasiliev is that you can write down a linear equation if you start and double these internal directions. Okay? So you introduce a new pair of twisters, which are the same type of object as the y's. Let's call them z alpha and z bar alpha dot. Don't confuse this with the Poincaré direction in the ADS metric. Nothing to do with that. It's just some internal z alpha and z bar alpha dot. Okay. And so here then you extend the star product. So the one with the y's are the same as before. And now in addition you have some rules for the z's. And okay, not going to write them all down. Let me just write down the general formula, which is the one useful for calculation. So you could write down a formula as the exponential of some differential operator, as I wrote before. Actually, in practice, what is more convenient is using an integral representation. This is equal to this will be all in the notes. So, and you can also find it in my review within. And this notation here, so now I'm starting dropping indices for simplicity, but this notation is just u alpha v alpha. So this is an integral over the twistor space. So these u and v's are the same object as y's and z's, right? We integrate over all the twistor space with this. For monomials, this reproduces this. Okay. I'm supposed to go to 10:15, Joao, right? But maybe I can take 10 more minutes. I want to at least write down the full equations. Okay. So this extended star product now admits some special objects which plays a role in the construction. So let me write it here. There is a special object called a Kleinian, which is usually denoted as kappa, and it's just E z alpha y alpha, and kappa bar is E z bar alpha dot y bar alpha dot. This satisfies some nice property that is squares to 1 with the star product. The same for the bar. And this is simple to prove using that integral representation. You can try if you want. And the important property also is that when we act on a function on the left and on the right, what this does is just switching the sign of the y's and z's, but not on the y bar and z bar. And the kappa bar will do the same on the y bar and z bar and not on the z's. Okay. And this operation of switching the sign has a name, conventional name, pi of f. So pi, take y bar, z and z bar, and just flips the sign. Okay. I'll see in a second where this shows up, but let me go here. Okay. So to summarize, in the fully nonlinear theory, we need to enlarge the twistor space, extend the star product to act on both y's and z's. This is not a new ingredient, it's just some property that this star product has once you have the z's and the y's together. That object doesn't exist, and if you didn't introduce the z's, there is basically no simple expression like this which does this job. Okay, and well, this is something that it's needed in nonlinear equations. Okay, so then the fields. So we already know that we needed W and B. Now they will have to be functions of Z and Z bar as well. Okay. And now because we have introduced this Z, this new Z direction, which is supposed to be something completely auxiliary, because at the end of the day, we know that all the physical degrees of freedom that we need in the theory must be contained in the Z-independent objects, W and B. So we introduced some extra auxiliary field S, which is just, it's a gauge field along these extra directions. Okay. And it has a gauge transformation. So now, okay. So now the gauge parameter will be a function of y bar, z, and z bar. And the gauge transformations gauge transformation on W is what you can guess. Now the only difference from before is that there is also the Z's and the star product acts on both. And transformation on this S. So this S is assumed to be like a gauge field in the Z direction. So it will transform as a gauge field with derivatives in the Z direction. This big Z is Z alpha, Z bar alpha dot. Okay. Plus S epsilon. Okay. And finally, so before when I introduced the linearized B field, I didn't say what kind of gauge transformation it had. So this B field is essentially like an adjoint field, but not quite. There is a twist. So the reason why you need this twist, historically, well, it comes by trying to rewrite Franzdal equations in terms of this field. And then you see that this is not quite an adjoint, but you need a twist. Make sure I got the signs right. Yes. Okay, where this, again, this pi is defined there. Pi of epsilon is epsilon minus y bar minus z bar. So if this pi was not there, this would just be the commutator of B with epsilon, and this will transform like a standard adjoint field. Now, to get the correct linearized equations, which we didn't see yet, but you can try to start and try to do it without the pi, and you'll see that you don't get anything. You just get empty equations. So to get the right equations, you need this twist. So this is called in the literature twisted adjoint, because it's not quite an adjoint. But so the nice thing is that we can use this kappa to realize explicitly what this pi is, and it follows that I don't need this. So if B is twisted adjoint, then an object phi, which is B star kappa, is just adjoint. So you can show that phi transforms just as a usual adjoint. Okay, so this fact then allows us to write down very easily a set of equations which are automatically gauge invariant and consistent. We know that field strength of gauge fields are in the adjoint, right? So let me write down. I need a big board. Okay, so now we have all the ingredients to try to write down the equation, guess the equations that we need. Okay, the simplest form of the equations is obtained if we combine W and S into a single object. So let's just do that. A is W and S, will be a gauge field in X and Z alpha, Z bar alpha dot directions, right? So the gauge transformation of this will be just this, where this guy is dx plus dz. Okay, so you can split this gauge transformation into x direction and z direction. You'll get W and S. But it's nice to put them together. And then the equations, once you have introduced all this machinery, look very simple, actually, very compact. And here are the equations. So you write the field strength for this A. What appears on this side must be something transforming in the adjoint. The only other field we have is B. B is not a joint, but B star kappa is a joint. So on this side we can put B star kappa, and well, let's put this plus B. Okay, so on this side you could write down any adjoint 2 form. This is one particular one, which is the one which does the job. Okay, you write something which only lives in these auxiliary directions, dz alpha, dz bar alpha dot. And as I said, the nice thing about this kappa is that this is now automatically transforms as an adjoint. So gauge symmetry transformation are consistent. This is a joint, that's a joint. And then you have an equation for B, which actually just follows from consistency. If you apply D on the first equation, Okay, so that's it. Okay, it's not okay. These are the Vasiliev equations. It's not quite it. We can do something more general. One can see that these equations are, well, so they are gauge invariant. That's obvious to see. After we have introduced all this machinery, the gauge invariance of this just follow from usual Yang-Mills rules. We know how everything transforms. Everything transforms in the usual way. So this is gauge invariant. And they are consistent in the sense that things like Bianchi identity on A is satisfied. It will impose some condition on this side, which holds if this equation holds, and vice versa. If you act with D on this equation, you get consistency with the first equation. So they are self-consistent and gauge invariant. We can actually do something more general. They remain consistent if we replace this with an arbitrary function of B star kappa. Bar, okay? And the equations are still consistent. Okay, so this is the most general bosonic Vasiliev equations in 4 dimensions. Okay, now they look simple. They are, of course, they are very complicated because there is a lot of stuff hidden here. These fields are functions of y bar z bar. If you start expanding these equations, they involve an infinite number of fields inside them. But once you have introduced this machinery, it's kind of natural to write down a system of equations which is gauge invariant at nonlinear level and consistent, right? Now, what is not clear is what does have to do with higher spins, right? It's not clear that this reproduces Fronsdal equations. But once you show that at linearized, if you start, well, first you have to identify some background of this, some solution. And if you start linearizing around that solution, you should recover Fronsdal equation. If you prove that, then you have shown that these are a nonlinear extension of Fronsdal equation. Because they give Fronsdal equation at linearized level, they have a gauge invariance, which is a fully nonlinear level. So they will automatically produce for you consistent gauge invariant interactions at a nonlinear level. Okay? But of course, we have to show that let's see. Maybe you think I can go up to 10:30? So what? Okay, so I go until 10:30. Is that okay? Okay. Okay. Okay, so let's try to explain a couple of things. So first, the freedom on this function f. So the function f, so there is a claim here that I'm not going to prove. F is not the most general function. You can make field redefinition and basically gauge away some part of this f by field redefinition, which are consistent with these equations. And the claim is that we can restrict f, this function f. Now schematically, let me write it f of x. It's understood that x is b star kappa. And to be precise, this function, it's meant to be a star function, which means that it has some Taylor expansions such that, something like b star kappa plus b star kappa star b star kappa and so on. Okay? So we can restrict f of x to be of this form. Where theta of x is just an even function. Okay, if you want to know more about this that I'm not going to prove, you can check this and this, for example, for a review of this. Okay, so we have an infinite family of Vasiliev theories parameterized by basically a choice of these constants, theta 0, theta 2, theta 4, and so on. There is a further restriction that we can do if we impose that the equations have a parity invariance. So if we impose parity invariance, then there are two choices. If we take B to be invariant under parity, B being an ordinary scalar field, then this restricts us, requiring that those equations are invariant under parity. Essentially, the only thing you have to check is that right-hand side is invariant. Under parity, Z and Z bar are exchanged. And if you impose that B transforms like this, f of x is restricted to be x. Okay, so this is called type A Vasiliev theory. This is what is dual to the scalar vector model in the three-dimensional boundary. Okay, that's dual to the scalar vector model in the singlet sector without Chern-Simons. Okay, if you instead require that B, you can require that B is not, that B changes a sign, that B is a pseudoscalar. Then parity invariance of the equations fix fx to be Ix. This is the type B theory, which is dual to the fermions. Okay, so I mentioned before type A and type B. This is what they are. So they are these equations where you take that f to be either just B star kappa in the type A or I B star kappa in the type B. Okay, and so type A will be B star kappa bar, and in the type B, I B star kappa minus I B star kappa bar. Okay, more generally, we have that family of theories which does not preserve parity, because these are the only two cases in which we can get a parity symmetry. So general theta 0, theta 2, theta 4 is a parity breaking higher spin theory. Okay, but if you recall our CFT discussions, this is precisely what we were looking for if we wanted some dual of vector models coupled to Chern-Simons fields, because those break parity. And now we see that there are such theories. They are just these more general theories with these extra parameters which break parity. Okay, so this theory will be dual to Chern-Simons plus vector models where these parameters will be mapped to the 't Hooft coupling of the Chern-Simons theory. And so on. Okay. Now, all the results that have been checked so far are consistent with the assumption that all these higher parameters are not actually there, and theta 0 alone is a function of lambda. Okay, so it seems like the most natural guess, because here we have a large family of theories parameterized by all these parameters, but on the CFT side, we only have one parameter, which is lambda. So although at the level of these classical equations of motion is not clear, a natural speculation might be that consistency of these theories at the full quantum level may actually require that these phases are not there and only the first one is there. Okay, but so that is not completely clear if it's true or not. What is true is that so far everything agrees with theta 2, theta 4, and so on equal to 0, and theta 0 equal either pi over 2 times lambda in the case of Chern-Simons plus scalar, or theta 0 is equal to pi over 2 1 minus lambda in the case of Chern-Simons plus fermion. Okay, so you can compute, for example, 3-point functions by extracting cubic interactions in these theories. You can compute 3-point functions, and you can, well, these 3-point functions only depend on theta naught, as it turns out, and they match known results in the Chern-Simons vector models if you have this map between theta 0 and lambda. Okay, I'm 1 minute above my proposed time, so maybe if you want, we can finish like 20 minutes or so in the discussion session. What I think is left to show is that there is a solution which is ADS, and then just explain a little bit how you would get Franzdal equations from there. Okay, so maybe we can do that in the afternoon. Okay. Any questions?
Was there any computation of something that would be sensitive to theta 2, for example, or just we never made anything?
Well, it's hard to, from CFT point of view, it's hard to say what depends on theta, what is theta 2. So if you compute, so from the higher spin point of view, from the bulk theory, this theta 2 will start affecting 5-point functions. 5-point functions. So you would need to compute 5-point functions. But yeah, so there is no actual computation that that can check that explicitly at this point. But it seems a natural thing that these parameters will not be there. If they are not there, then from the Vasiliev theory, you can prove basically that there is a duality between these theories and these theories just by changing lambda and 1 minus lambda. From bulk theory, that would be manifest if there is only this theta 0 and it depends on lambda in this way, because it's just the same equations of motion, you just relabel theta naught. And this duality between these theories has been checked not only at the level of 3-point functions, but also at the level of thermal free energy. So thermal free energy is presumably a more, it's a more complicated observable. If we could compute the thermal free energy from the bulk, it may depend on these parameters. It tells you that all parameters should have this. That could be an option. Yes. Yes. Yeah. Yeah. Yes. So what has been computed is the thermal free energy on the plane. So you put the CFT on R2 cross S1, S1 is the temperature. Yeah, so that should correspond to finding here some black brane solution and compute its free energy. Just if we had a Lagrangian, you would just compute the classical action, and that would be the leading contribution to the free energy. But we don't have a Lagrangian, and such solutions have not, this black brane solution have not been found. Yeah.
Did it say anything like if you swap lambda with A minus lambda,
Sorry, yes. So you see that this are related by lambda going to 1 minus lambda, right? That's in terms of the Chern-Simons theory, it's a level rank duality. It's the same as exchanging n and k. So at the level of 3-point function, you can see that this Chern-Simons plus scalar and Chern-Simons plus fermions, they map into each other if you do this. This would take me a little bit longer time to explain fully, but one has to be a little bit more careful. So because you're asking, let me try to state this duality more carefully. The duality is really between Chern-Simons coupled to fermion. You send lambda to 1 minus lambda. You get Chern-Simons coupled to the critical scalar. So this means that on this side, what we discussed yesterday, you have the Chern-Simons coupled to scalar deformed by a phi to the 4th interaction and flow to the IR. That CFT corresponds to this. Why we need to do this? It's because here we have a scalar operator of dimension 2. In there, if we didn't go to this critical point, we would have a scalar operator of dimension 1. But now we have a scalar operator of dimension 2. And this duality just acts on lambda, so it's not supposed to change the dimension of the operators in the spectrum. Okay, and you can also have the critical psi that would be dual under this duality to the ordinary scalar coupled Chern-Simons. So in the Vasiliev side, so these theories would be this parity breaking invariant theory with theta naught and the scalar field quantized with delta equal to 2 boundary conditions. So you're not changing the boundary condition in this duality. You just relabel the map between theta and lambda. And the same here. Here you will have delta equal to 1. Remember that in the Gross-Nouveau model, you have delta equal 1 in the fixed point. If you had Chern-Simons, you still have delta equal 1 plus 1 over n corrections. And here, delta equal 1. Okay? Any other question? So as I said, this was checked at the level of 3-point functions and the level of thermal free energy. Thermal free energy will be scale like n. There is a function of lambda, and there is a power of the temperature. What's the power?